I am really excited about video number 8 for that most beautiful subject in math, complex numbers and complex analysis. Why am I so excited? Because we're going to start to learn about complex multiplication. We'll keep it simple here in this first video about complex multiplication. We'll just multiply by the imaginary unit I, but even that is pretty amazing. It's got some very interesting geometric interpretations that we want to explore, discover, and hopefully take joy in. As in video number 7, I also want to put this in the broader context of math, in particular linear algebra and linear transformations defined by matrix multiplication. Let's start by letting z equal an arbitrary complex number, x plus I times y, where, as we've seen before, x and y are taken to be real numbers, and I is the imaginary unit, defined by the property that I squared equals -1. And let's ask ourselves, what should it mean to multiply z by I? Let me call the answer w equals I times z equals I times x plus iy. Essentially, let's explore what would happen if we treat these expressions as essentially polynomials in x, y, and I, with the caveat that we also want to replace I squared by -1. Go ahead and assume the distributive property works. Multiply both of these things by I to get I times x plus I times y, which would be I squared times y. Go ahead and replace I squared with -1. We could then write this as I times x plus, well, -1 times y, which would be more natural to write as I times x minus y. And that is certainly fine. However, we usually want to have the real part first plus I times the imaginary part next. So we're going to rearrange and write this as -y plus I times x. Essentially, when multiplying I times an arbitrary complex number z equals x plus iy, we are saying this is what we think we want to do, and now we want to explore the consequences of this. One pretty immediate consequence that you see by thinking about the concept of the modulus, or absolute value of a complex number, is that w, I times z, has the same modulus, the same distance to the origin as a point, or the same length as a vector, as z does. Why? Go ahead and compute the modulus of w, compute the modulus of -y plus I times x. By definition, that's the square root of the real part, quantity squared, plus the imaginary part, which does not include the I, it's the x there, quantity squared. We know that, well, when you take a real number and negate it and square it, you get the same thing as that real number itself squared. This is square root of y squared plus x squared. Then you can use the commutative property of addition, write this as square root of x squared plus y squared, and that is the same as the modulus of x plus iy. It is the same as the modulus of z. So w, which again is I times z, has the same modulus as z does. It's the same distance to the origin as a point. As vectors, these two arrows have the same length. That's one important geometric property to realize. There's another very important geometric property to realize that we will see as we study an example next. For our numerical example, I'm going to consider my favorite complex number, z equals 4 plus 3i. It's a nice complex number where the distance to the origin, the modulus, is square root of 4 squared is 16 plus 3 squared is 9, square root of 25 is 5. If I plot this as a point and a vector, what do I get? I'm going to treat this as one unit here. So I go 1, 2, 3, 4 units to the right, and 1, 2, 3 units up. As a point, it's that dot right there in the complex plane. And as a vector, it's this arrow, which has a horizontal displacement of +4 and a vertical displacement of +3. Those displacements are also sometimes called components. And if I wanted to, and I will, this will be helpful for later in the video when I talk about matrix multiplication, I could think of this as a column vector with components 4, 3 written like that. Where in this picture will be w equals I times z? It's going to be over here. Maybe you want to figure it out before I do. W equals I times z is I times 4 plus 3i. Multiply the I through, that gives me 4i plus 3i squared. Remember, I squared is -1. Rearrange, this is the same as -3 plus 4i. So we move 3 units to the left. The real part is -3 as a vector. That means the horizontal or first component is -3. and the imaginary part's positive 4. I go 4 units up, so that's going to bring me right there. There is where W is as a point. As an arrow, I draw this one from the origin to that point. That is the vector for W. We've done some exploring. Have we discovered anything? Look at the picture. It looks like maybe, just maybe, this angle right here is a right angle. It looks like it's 90 degrees or pi over 2 radians. Is it? I actually have a protractor, and let's go ahead and measure this angle with a protractor, but then we'll also use some trigonometry to confirm the answer. Now, of course, I didn't draw this perfectly, so this may not be perfect. Got a protractor here. I put this line along that arrow right there, and if I imagine extending this arrow right here, it does seem to be pointing very closely at that 90, a 90-degree angle. It does seem like this is probably a right angle. Is that related to the fact that the imaginary unit I, which would be right here in the complex plane, as an arrow would be right here, is at a 90-degree angle with the positive real axis? Yes, it is related to that. It's amazing. But now let's go ahead and use some trigonometry and a calculator to confirm this numerically. I'll draw a couple right triangles in here. One right triangle there, one right triangle right here. Focus on this right triangle. This side has length 4, this side has length 3. Of course, the hypotenuse has length 5. And what is this angle? Let's label it with the Greek letter alpha. What is alpha? Well, from your trigonometry, so katoa, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent, toa, is opposite over adjacent. The tangent of alpha is going to be 3/4. So alpha itself could be represented as the inverse tangent of 3/4. It's not a nice number. Let's go ahead and just approximate it with my calculator here. If I use my inverse tangent button right here, I am in radian mode. If I do inverse tangent of 3/4, which is 0.75, I get about 0.6435 radians. I am in radian mode. If I multiply that by 180 divided by pi, that will convert it to degrees. This is about 36.87 degrees. What about this right triangle over here? Of course, the first component, or real part of this complex number, is -3, but as a distance here, that's +3, and as a distance here, that's +4. What is this angle? Let's call it beta. By the same kind of reasoning with trigonometry, beta is going to be the inverse tangent of the opposite over adjacent, inverse tangent of 4/3. Use our calculator for that. Inverse tangent of 4/3 in radians is about 0.9273 radians. Multiplied by 180 divided by pi for degrees, that's about 53.13 degrees. If I add up alpha and beta, 53.13 degrees and 36.87 degrees, maybe you can do that in your head, you do get 90 degrees. 36 point, I'll go ahead and use the full decimal places here, 9.9765. I do get 90 degrees. It looks like we've numerically confirmed, it seems to be the case, that alpha plus beta is 90 degrees. In radians, you can check that turns out to be pi over 2 radians. It is a right angle right there. It does seem to be the case. Is there a way we can really prove this? This is just numerical evidence. Well, if you know about dot products from linear algebra and facts about dot products, that's the quickest way to prove it. This complex number as a column vector can be represented by -3, 4. And if you take the dot product of these two vectors, -3, 4, dotted with 4, 3, that's where you multiply the corresponding components and add the results. It's a very important operation in linear algebra. It's got tons of applications, including to data science and artificial intelligence and so forth, but I'm not going to get into details. -3 times 4 is -12. Add the product of these components. 4 times 3 is +12. You get -12 plus 12 is the number 0. And the fact that you've got these two non-zero vectors whose dot product is 0 is enough, if you know some linear algebra, to say this angle is 90 degrees. It's a right angle. We say these vectors are perpendicular or orthogonal to each other is the more official word. This is just as easy to prove more generally. Once again, we go back to thinking about z as x plus iy. In terms of vector notation, that would correspond to the vector with components x and y. And w was I times z. That was, again, as we saw here, negative y plus ix. In terms of column vectors, that would be a column vector with components negative y and x. And if we take the dot product of these two vectors, multiply the first components, x times negative y is negative xy. Multiply the second components, y times x is xy. Add the results, we get 0. And if either x or y is non-zero, we've got non-zero vectors here whose dot product is 0. These vectors are going to be perpendicular or orthogonal to each other. So I times z has the same modulus as z does, and it's at a 90-degree rotation from z, in fact. 90-degree clockwise rotation. I haven't really proved that it's a clockwise rotation, though we saw it with that example, but it is at a 90-degree angle. Now let's explore this even more in terms of linear algebra in a way that's going to help us use Mathematica at the end to make some pretty cool animations. I'm really excited about that too. Let's go ahead and use function notation. And as in video number 7, I'm interested in thinking about things in terms of real and imaginary parts, ultimately two-dimensional vectors, ultimately writing these functions that I'm going to write down in terms of linear transformations. So I'm interested in the function w equals f of z equals I times z. What are the real and imaginary parts? We've already seen it. Let's use the notation from the last video. Replace w with u plus iv, very standard thing to do in complex analysis. Replace z with x plus iy. Go ahead and multiply I times x plus iy as we've already done. You'll get negative y plus I times x. That corresponds, if you think in terms of column vectors, to the vector equation uv equals what? The real part u equals this real part, negative y, and the imaginary part v equals this imaginary part x. I can then take this vector and write it as a linear combination with x times a vector first plus y times another vector second. I can write this, if you think about it, as x times the column vector 0, 1 plus y times the column vector negative 1, 0. The benefit of doing this, especially if you look it up in linear algebra books, especially by Lay, for example, is that this is essentially the definition of matrix multiplication, where the 2 by 2 matrix that I have will have this as the first column and this is the second column, 0, 1, and negative 1, 0, and that's getting multiplied by the column vector whose components are x and y. I can give this matrix a name if I like. I could call it A sub f, capital A meaning it's a matrix, and sub f meaning it's corresponding with the function f. I could also call this T sub f of, well, if I want to give this vector a name, well, I should probably call it z. T sub f of z gives me this vector uv, which I could also call w. I'm abusing notation a bit. I'm treating w and z as both complex numbers and column vectors. We can be okay with that kind of abuse of notation. This confirms that this complex function does correspond to this real function of the real plane that is a linear transformation, and we can use tools from linear algebra. One such tool helps us put this in the context of rotations in general. Your general rotation matrix, and this is some knowledge that you'll have if you study linear algebra, has this form. It's a 2 by 2 matrix whose first column is cosine of theta and sine theta, and whose second column is negative sine theta, cos theta, where what is theta? Theta is some arbitrary angle. If it's positive, it corresponds to a counterclockwise rotation. If it's negative, it corresponds to a clockwise rotation, as is usual in math. And if you replace theta with 90 degrees, pi over 2 radians, what do you get? You get cosine of pi over 2, sine pi over 2 for the first column, and then negative sine pi over 2, cosine of pi over 2 for the second column. Remembering your trigonometry, Cosine of 0 is 1 and sine of 0 is 0. If you go up to a pi over 2 angle in radians or 90 degrees, cosine of 90 degrees becomes 0 and sine of 90 degrees becomes 1. This matrix is 0, 1, negative 1, 0. It corresponds exactly to this matrix that you see right here. That was the matrix for this linear transformation. It's geometrically describing what goes on with this particular function right there, confirming, at least if you believe this general rotation matrix, that this is rotating by 90 degrees, in fact, counterclockwise. There's other cool things that we can do here. We can consider other functions, as we did in video number 7. I could also consider the function w equals, how about negative I times z? I hope you realize that that is going to be the inverse function of this, and I'm in fact going to use inverse function notation right away. W equals f inverse of z equals negative I times z. Why is that the inverse function of this? Well, what happens when you compose them? F of f inverse of z is I times negative I times z, right? Because f of a quantity is I times the quantity. I'm applying f to this, which is this. So I've got I times that quantity, I times negative I times z. That's negative I squared times z. That's negative of negative 1 times z. That's positive 1 times z, or z itself. We are getting the identity function back. These are truly inverses in that order. They're inverses in the other order too. F inverse of f of z would be negative I times iz, giving us ultimately the exact same thing. These two functions are inverses. Now, what does that mean geometrically? This function rotates around the origin counterclockwise by 90 degrees. This function's got to get you back where you started. That must be a clockwise rotation by 90 degrees. And oh, that makes sense geometrically too. You think about the complex plane. There's your real axis, here's your imaginary axis. Remember, I was up here and negative I is down there. The angle for I with the positive real axis is positive 90 degrees, and the angle for negative I with the positive real axis is negative 90 degrees. That corresponds to a clockwise rotation. We could combine this with complex conjugation. We could let g of z be, for example, z bar. We could ask, what does it mean to compose f of g of z, and what's the geometric effect of that? F of z again takes I times the input, so here this is going to take I times z bar. That's going to be the formula for this in terms of I and z. If we want to think in terms of real and imaginary parts, we could do so. I times the conjugate of x plus iy, that's I times x minus iy. Multiply the I through, we'll get ix plus I times negative I is positive 1 times y. That would be y plus ix. In terms of vector notation, what are the real and imaginary parts going to be? They're y and x in that order. I could rewrite this vector as x times 0, 1 plus y times 1, 0. And ultimately, by definition, that's the matrix whose first column is 0, 1 and whose second column is 1, 0 times xy. And you could think about this on your own. This corresponds pretty nicely to a geometric effect as well. This corresponds to reflecting across the line y equals x in the complex plane. If you've got a complex number z and you apply this operation, z bar times I to it, ultimately it's going to reflect across this line y equals x and bring you over here. That's going to be I times z bar. You could think of that in terms of composition of functions as well. You could think of that as being, take z and first reflect it across the horizontal real axis, because that's what complex conjugation does, before rotating it counterclockwise by 90 degrees. All these things have amazing connections. And I could confirm these computations with matrix computations by multiplying matrices. I won't take the time to do that. I would encourage you to do so. We end, as usual, with some pretty cool things in Mathematica. First of all, I want you to know that Mathematica does have rotation matrices built in, and if I enter this code here, rotation matrix theta, plugged into the matrix form, which displays the output as a matrix, I get that matrix that I showed you a few minutes ago. I can make use of that to do some pretty cool visualizations. First of all, I can visualize I times z, negative I times z, and I also put negative z in there. We're going to see a pretty cool picture here where I've got z at an arbitrary point indicated by this locator command right here. I see I times z is this 90-degree counterclockwise rotation from z. I see negative I times z is this 90-degree clockwise rotation from z. Negative z is over there. That can be thought of as a reflection across the origin. That's the simplest thing to do, but it also could be thought of as a rotation, either by 180 degrees counterclockwise or 180 degrees clockwise. I also emphasize that I times z can be thought of as negative I times negative z, so you could start at negative z and go 90 degrees clockwise. And likewise, negative I times z could be thought of as I times negative z, so you could start at negative z and go counterclockwise. And locator also allows me to change the initial vector, the initial location for z. You also see a circle centered at the origin, emphasizing that these points are all the same distance to the origin. They all have the same modulus. This code down here allows me to visualize even more. This gets a little confusing, but we are visualizing all these quantities right here. I've got in darker colors z, I times z, negative z, and negative I times z. And then in lighter colors, I got the conjugate involved. I times z bar right there in light blue, z bar right there in pink, negative I times z bar right there in light green, and negative z bar right there in sort of a light orangish pinkish there. And look at this. You, for example, see that z and I times z bar are indeed reflections across this line of y equals x. You could also notice that, for example, z bar and negative I times z are reflections, these two vectors right there are reflections across this line of y equals negative x. And that's true no matter what point you're starting at. I can even move it around this way and see how all these things are related to each other. It's a pretty amazing animation with lots of beautiful symmetry to it. And finally, I can confirm the linear algebra that we did. If you want to pause the video and look at what I've got here, I'm talking about matrices and linear transformations. I can confirm various calculations that you can check with what I've written here. I can enter some functions, and then I can run this code. And here, it's similar to the last video. These three different sliders are going to have three different geometric effects. If I move the lambda 1 slider, it takes the original point and rotates it counterclockwise by 90 degrees, representing multiplication by I. If I move the lambda 2 slider, it takes the original point and rotates it by 90 degrees clockwise. That's the green arrow there. And finally, if I do the lambda 3 slider, it's a little bit more complicated. This is going to involve z bar and then times I. So first it's going to reflect across the real axis, and then it's going to rotate counterclockwise by 90 degrees. So watch it here. That orange vector first reflects across the real axis, and then when I get the slider moves halfway, now it starts rotating by 90 degrees to give me that point that is the reflection of the original point across this line of y equals x. And it doesn't matter where I start, all these properties still hold. That was a lot of fun for me. I hope it was fun for you. Strength and honor to you.